Welcome to The Explainer. So let's dive right into what I think is an absolutely fascinating foundational concept in AI. We're talking about automated planning. Seriously, how does a machine actually know what to do next? Today we're exploring exactly that by looking at how strips planning models actions.
To get things started, we really have to ask ourselves, how do we teach a machine to sequence out a complex task? As humans, we sequence things out without even thinking about it. Making coffee, driving to work, you name it. But for an AI, well, we need a mathematical, highly structured language to represent the world, define a goal, and map out the exact steps required to get there without making a catastrophic mistake.
Here is our roadmap for today. We'll be looking at 1. Classical planning, 2. Strips actions, 3. Mapping actions, 4. Mutex actions, 5. Hierarchies, and finally, 6. The future of strips. Let's jump right in.
Let's start right at the foundation, setting the rules of the world our AI operates in. Section 1. Classical planning. The planning problem.
There is a massive difference between the perfectly predictable world of classical planning and the, let's say, chaotic world of contingency planning. In classical planning, everything is a known quantity. We've got a single agent, the actions have zero duration, and there's a unique, unambiguously known initial state. It is perfectly deterministic, meaning if I do X, Y will absolutely happen, for sure. Contingency planning, on the other hand, that's a lot more like real life. Sensors might be faulty, information is incomplete. For instance, if it rains, the agent might need to suddenly pull out an umbrella. But for our purposes today, we are staying firmly in the highly predictable, comfortable realm of classical planning, where plans can just be a clear, simple sequence of actions.
Right, now that our rules are set, let's zoom into the core of this explainer. Section 2, Strips Actions and the Anatomy of Actions.
This quote brilliantly illustrates exactly why we still care about strips today. It is the ultimate baseline representation for problem solving. By the way, STRIP stands for the Stanford Research Institute Problem Solver. Even in 2025, it gives us this compact, strictly structured way for a planner to search for a sequence of actions that transforms an initial world into a goal state. It literally forces us to think purely in terms of symbolic, propositional representation.
Think of these as the 3 vital organs of any action. What needs to be true first, what becomes true after, and what is no longer true. First up, preconditions. These are the absolute facts that must hold before the action can even execute. Second, add effects, the facts the action actually makes true. And third, delete effects, the facts the action makes false. Let me give you an example. If a robot picks up a block, the precondition is that its gripper has to be empty. The add effect? Well, it's now holding the block. And the delete effect? The gripper is no longer empty. It's wonderfully simple, but it forces absolute logical clarity.
So now that we have our atomic action, how do we actually sequence it together with others? Section 3. Mapping actions and graphs in planning.
The crucial takeaway here is that a plan graph is what visually organizes our timeline. It neatly separates the state of the world from the actions being taken. It's this alternating structure. Even-numbered levels represent propositions, which are basically just the facts that are true at that exact moment, and they're drawn as dots. Odd-numbered levels represent the actual actions we can take, which are shown as boxes.
We rhythmically build this graph outward, literally layer by layer, carrying forward unused truths using what we call maintenance actions. We start at layer 0 with our initial conditions. Then layer 1 contains all the actions whose preconditions are met by those initial facts. From there, we generate layer 2, capturing all the effects of those layer 1 actions. But, and this is key, if a fact was true at step 0 and we didn't do anything to delete it in step 1, a maintenance action simply connects it forward. This just ensures our AI doesn't forget facts simply because a moment passed.
But what happens when our building blocks collide? Let's move to Section 4, Mutex Actions or Exclusive Actions.
You can think of this as conflict resolution for AI. If any of these 3 conditions occur, our actions are mutually exclusive, or mutex, which means they absolutely cannot be executed at the exact same time. The first condition is inconsistent effects, meaning the effect of one action is the direct negation of another. The second is interference. This is where one action deletes the precondition of the other, meaning obviously you can't possibly execute them together. And the third is competing needs. This happens when 2 actions require preconditions that were already mutually exclusive at the previous level. By clearly defining these rules, the system can sweep forward through a graph, cleanly calculating conflicts one layer at a time.
Now, let's see how this all builds into massive systems
called Hierarchical Task Networks, or HTNs. Section 5. Hierarchies, Scaling Up Tasks.
Picture a single primitive node as just one of our base-level strips actions living within a much, much larger library. This is the absolute base level, an executable step with very clear preconditions and effects. But to solve complex real-world tasks, an agent can't just think in primitive steps. It needs to think abstractly too.
HTNs scale up by mixing these primitive actions with non-primitive actions, which are basically just abstract goals that still need to be broken down. Non-primitive actions have external preconditions and external effects. Think about it. An AI can't just execute build a house. That's way too broad. It has to use action decomposition to break that massive abstract goal down into the final plan, which eventually only contains those primitive executable operators.
To actually solve a plan, we decompose these larger abstract goals into a correct, consistent sequence of these smaller primitive actions, and we dynamically calculate the causal links between them. We break down the abstract goal node over and over until we are left with a perfectly ordered, conflict-free sequence of primitive nodes. This dynamic calculation means actions from one abstract operator can safely be interleaved with others, which keeps the entire plan flexible and super robust.
Finally, let's bring it all back to the present day. Section 6, the future of strips and usage in 2025.
When you're engineering these systems, there are some major pitfalls you absolutely have to avoid. Missing a simple delete effect can literally derail an entire automated plan. Beginners frequently specify their add effects but totally forget the delete effects, which creates these unrealistic, overly optimistic models. Another massive pitfall is overlooking implicit assumptions, like, say, forgetting to explicitly state that an object can only be in one physical location at a time. The solution is always to make your invariant explicit as facts. You literally have to tell the machine everything.
You might be wondering, with all our modern AI complexities, does this still matter? Oh, absolutely. Starting with this minimal, well-structured representation gives researchers the conceptual scaffolding they need before moving into continuous or highly uncertain environments. In 2025, strips still serves as the absolute foundation for state space search. It helps newcomers understand goal regression and plan validation. It's heavily relied upon to benchmark planner performance reproducibly. And it drives incredibly powerful search heuristics, like delete relaxation, which helps planners efficiently estimate the cost to reach a goal. Simply put, it is an indispensable tool for discrete prototyping.
I'll leave you with that thought. Actually, thinking in strips can seriously clarify your own real-world tasks. What are the strict preconditions for your next big project? What exactly will your actions add to your world, and what will they delete? Understanding exactly how actions modify the state of the world really is a superpower. Thank you so much for joining this explainer, and keep exploring.